Welcome to the boardroom. Listen, today we are not just studying physics. We are strategizing for absolute total Cambridge exam dominance. I want you to treat this explainer exactly like you are the CEO of your own academic career. And the examiner? Well, they're the board of directors you need to win over. You've got to justify every single point with precise data, clear logic, and an absolutely unbeatable strategy. We are focusing heavily on syllabus codes 0625, 0651, 0652, 5054, and 9702. To really illustrate our challenge today, I've actually pulled a real, highly failed Cambridge Physics past paper question regarding forces and motion. Now, before we tackle it, let me introduce you to two archetypal students I see all the time. First, we have Alex. Alex is the overloader. Alex spends hours memorizing the textbook and just dumps raw physics facts onto the exam page, hoping something sticks, but offers absolutely zero analytical structure. Then we have Sam. Sam is the rusher. Sam completely misses the specific requirements of the examiner's command words, rushing the answer and ends up dropping crucial marks despite actually knowing the underlying science. Look at their flawed answers side by side in your head, those glaring red pen marks everywhere. We are going to transform those mistakes into a foolproof winning strategy. Okay, let's dive right into this and construct your blueprint to logically master Cambridge IGCSE Physics concepts regarding forces and motion. Here is our strategic roadmap to systematically conquer this topic. We're hitting 6 core modules: the rules of motion, mass versus weight, surviving the fall, going in circles, momentum and impact, and finally, the examiner's lens. Let's jump right into Module 1.
Section 1. The rules of motion. We're looking at exactly how unbalanced forces change motion. Okay, before we even think about looking at dynamic examples, we need to strictly define our core vocabulary. In our boardroom, precision is literally everything. You can't pitch a vague idea. So the Newton, denoted by a capital N, is strictly defined as the force required to give a mass of 1 kilogram and acceleration of 1 meter per second squared. Got it? Now the resultant force, this is absolutely critical. It is the single force that has the exact same effect on a body as 2 or more forces acting together. Now, let's look at how our student Alex handles a question asking for this specific definition. Alex writes, resultant force is when forces push together on a thing. Red pen. No way. That is way too vague for Cambridge. The examiner needs the precision of single force and same effect. Remember, forces appear when 2 objects interact. You lift an apple, that's roughly 1 Newton of force. But what if you launch a giant space shuttle off its pad? The booster rockets are supplying several million newtons of initial thrust. As that spacecraft accelerates upwards, the crew experiences being pressed firmly back into their seats. Why? Because massive unbalanced forces are at play. Now, this diagram brilliantly illustrates our point in a more everyday terrestrial setting. Notice the car moving along the road. Forces, remember, are vectors. They have both magnitude and a specific direction, which we represent here by arrows. A forward force provided by the car's engine causes the car to speed up or accelerate. But if the driver suddenly applies the brakes, a backward friction force makes it slow down or decelerate. And what if the driver turns the steering wheel? A sideways force causes the car to fundamentally change direction. Now, here is exactly where our other student, Sam, rushes and loses marks. The exam question explicitly asks, describe 3 ways a force can change the motion of an object. Sam just writes, it makes it move. Another red pen. The strategic answer, the one that secures absolutely all the marks, explicitly states 3 things. A force can change speed by accelerating, change speed by decelerating, and change the direction in which an object is moving. Precision matters. So it's absolutely critical to contrast what happens to an object's motion when forces are perfectly balanced versus when they are unbalanced. Examiners frequently test this exact distinction. This brings us to the ultimate exam strategy framework that top-tier students use to structure their physics answers. We call it the PEEL framework. That stands for point, evidence, explanation, link. Think of it as your secret weapon. When forces are balanced, the resultant force is exactly 0. The object either remains completely at rest or it continues at a constant speed in a straight line. But when forces are unbalanced, the resultant force is greater than 0, and the object accelerates, decelerates, or changes direction. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's put PEEL into practice. If a question asks you to explain the motion of a car with 600 newtons of engine push to the right and 600 newtons air resistance to the left, you don't just guess, you use PEEL. Point, the forces are balanced. Evidence, 600 newtons forward minus 600 newtons backward equals a resultant force of 0. Explanation, because the resultant force is 0, there's absolutely no acceleration. Link, therefore the car continues at a constant speed in a straight line. Do you spot how incredibly structured and professional that is compared to Alex's raw fact dump? That's how you get the grade. Let's move to Section 2, mass versus weight, distinguishing two incredibly crucial quantities.
This matrix right here, it visually locks in the boundaries between mass and weight. Honestly, memorize it. Confusing these two is one of the most common stumbling blocks I see. Mass is simply the amount of matter in an object. It's measured in kilograms, and the kicker is it is unchanged regardless of where you are in the universe. It's the intrinsic property of an object that resists any change in its motion. Weight, however, is a force. It is the actual gravitational pull acting on that object. Because it's a force, it's measured in newtons, and it totally changes depending on the specific gravitational field you happen to be in. Think about it like this. If you take a 70-kilogram astronaut and teleport them to the moon, their mass remains exactly 70 kilograms because they are made of just as much physical matter as they were on Earth. However, because the moon's gravitational pull is much weaker, their weight, the downward force they exert on the ground, will be significantly less. In an exam, if Alex is asked for the weight of a 2-kilogram object on Earth and just writes 2 kilograms, that is an instant failure to understand the examiner's objective. You must calculate the force.
And to actually calculate that force, you need to keep this vital, non-negotiable number in your head, 9.8 meters per second squared. This is the acceleration of freefall, or the acceleration due to gravity close to the surface of the Earth, usually denoted by the symbol lowercase g. Because the Earth pulls with the exact same force on every single kilogram of matter, every object falls with the same acceleration, assuming we ignore air resistance for a moment. If you drop a massive 5-kilogram bowling ball and a tiny 1-kilogram ball off a building at the exact same time, they hit the ground simultaneously. To find weight, we use your new best friend, the equation, weight equals mass times the acceleration of freefall, W equals m times g. So an object with a mass of 1 kilogram has a weight of roughly 9.8 newtons down here on Earth. And here is a pro tip where students lose marks. Always, always verify your units. If an exam purposefully gives you a mass in grams to trick you, you must divide by 1,000 to convert it to kilograms, the base SI unit, before you even think about calculating weight in newtons. Don't fall for the trap.
Moving on to Section 3, Surviving the Fall. We're looking at terminal velocity and air resistance.
Now, I want to do a little 60-second visual data scan challenge with you. Look at this speed time graph. It visually maps the exact second-by-second physics of a falling parachutist. We are going to do a live transformation of a bad answer here. Let's say the exam asks, explain the motion of the parachutist before the parachute opens when reaching maximum speed. Alex, our overloader, originally wrote, the parachutist falls fast, gravity pulls them down, and air pushes up until they stop speeding up. While intuitively that sounds okay to a layperson, it lacks absolutely all the required scientific rigor for the Cambridge board. It's too casual. Let's rewrite this using our PEL blueprint. Point. Initially, the weight is greater than the air resistance, causing a downward acceleration. Evidence. As the speed increases, the upward force of air resistance also increases. Explanation. Eventually, that upward air resistance exactly balances the downward weight, making the resultant force zero. Link. Therefore, the parachutist stops accelerating and reaches a constant maximum speed, which we scientifically define as terminal velocity. Boom. That right there is a 100% mark potential answer. It justifies the physics perfectly. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, back to the boardroom. Now, ask yourself this crucial exam question. If the speed time graph is sloping upwards, which of the two forces acting on the parachutist is actually greater? Sam rushed this exact question in a past paper and wrote, air resistance because they are going up. Incorrect. Sam completely failed to analyze what the graph was showing. A sloping upwards line on a speed time graph means the object's speed is increasing. It is accelerating downwards towards the Earth. It does not mean the person is physically moving upwards. If they are accelerating downwards, the downward force must be winning out. So the correct boardroom-ready answer is that the weight is greater than the air resistance during that upward sloping phase. Always, always let the data dictate your strategy, not your gut feeling. Let's shift gears to Section 4, Going in Circles. We are talking about forces perpendicular to motion. This concept trips up so many people. When a car turns a corner, or say a kid spins an apple on a string around their head, the object is moving at a steady speed, sure, but it is constantly changing direction. Because velocity is a vector, meaning it cares about both speed and direction, a change in direction means an automatic change in velocity. And what do we call a change in velocity over time? Acceleration! So it's accelerating, even if the speedometer reads a constant 30 miles per hour. Therefore, an unbalanced force must be actively pulling towards the center of the circle,
perpendicular to the motion to keep it from flying off in a straight line. Now, scan the data points on the screen. A bigger resultant force directed toward the center is required if what? First, if the object's mass is bigger. Imagine it. A tiny insect is much easier to deflect into a circular path than a massive charging rhinoceros, right? Second, if the object's speed is bigger. You physically feel a much bigger force pushing you into the side of your car door when you take a bend at 60 miles per hour compared to 10 miles per hour. Third, if the radius of the circle is smaller, meaning the bend is much sharper. Mastering these 3 specific conditions allows you to perfectly predict exam outcomes when the board asks you how changing variables affect the required centripetal force. Next up, Section 5, Momentum and Impact. Calculating force, mass, and velocity. Okay, focus up, because now we face the final boss of our blueprint, the demanding calculations behind momentum and impulse. First, let's absolutely lock in the definitions. Momentum, denoted by a lowercase p, is the quantity of mass multiplied by velocity. Impulse is defined as the change in an object's momentum, or the force acting on an object multiplied by the time interval for which it acts. The core equation is impulse equals F times delta t. Now we're going to do a quick find the flaw challenge. Consider this flawed sample paragraph from a mock exam, and I want you to identify exactly why it loses marks. When a heavy car crashes, it has high momentum. The seatbelt reduces the force on the driver by making the momentum change faster. This keeps the driver safe. Did you spot the fatal flaw? Let's check with some real examiner commentary. The phrase, making the momentum change faster, is completely physically wrong and loses all the analysis marks. The entire purpose of a seatbelt or a crumple zone in a car is to actually increase the time over which the collision occurs. Because impulse equals force times time, if you increase the time, that's delta t, taken to bring the driver's momentum down to 0, the average force F acting on the driver's frail body is significantly reduced, minimizing injuries. You must always justify the safety mechanism with the impulse equation.
Let's move into a quick speed writing drill. We are going to walk through the exact steps of a calculation, and you need to adopt this perfectly structured layout in your exams to guarantee you never drop a single method mark. Consider this worked example. You strike a tennis ball with a mass of 0.10 kilograms, giving it an instant acceleration of 500 meters per second squared. What resultant force is needed? Step 1. Write down exactly what you know from the prompt. Mass equals 0.10 kilograms. Acceleration equals 500 meters per second squared. Step 2. State the equation and substitute your numbers. Force equals mass times acceleration. F equals m times a. Step 3. Calculate and state the final force with its correct units. 0.10 multiplied by 500 equals exactly 50 newtons. Listen to me. Whether you are calculating a tiny 50 Newton force on a tennis ball or the massive 2.29 meters per second squared acceleration of an Airbus A380 with a mass of 560,000 kilograms, your layout remains rigidly identically the same. This system protects you from simple, silly arithmetic errors that cost Sam the entire question.
But wait, what if forces do not act along the exact same straight line? What if they are perpendicular, pulling at a 90-degree angle to each other? You can't just add or subtract them simply. You must transition to a graphical method. This step-by-step vector triangle method on screen is your guaranteed way to accurately find the resultant force without complex trigonometry. First, choose a very precise scale, like 1.0 centimeter on your ruler equals 1.0 Newton. Second, draw your first force arrow perfectly to scale, indicating its direction. Third, starting exactly from the tip, or the pointy end, of the first arrow, draw the second force arrow. Fourth, complete the vector triangle by drawing the resultant arrow from the very start of your first arrow straight to the very tip of the second arrow. Finally, measure this new resultant arrow with your ruler and convert it back to newtons using your chosen scale. It is a mechanical, totally foolproof process if you just follow the blueprint. No rushing like Sam, no guessing.
Finally, Section 6, the examiner's lens. We are going to master Cambridge command words. This quote, pulled straight out of the Cambridge syllabus documentation, highlights a totally crucial difference. You can know all the physics facts in the world, just like Alex, but if you don't answer the specific command word, you fail the pitch. The board will reject it. The command word calculate means to actually work out the answer from given facts, figures, or information. It strictly requires numbers, shown working out, and units, period. But the command word explain means you must set out purposes or reasons, or make the underlying relationships between things evident. You have to provide the why and the how, fully supported by scientific evidence. When Sam sees a question like, explain why a falling parachutist reaches terminal velocity, and Sam just quickly scribbles because air resistance equals weight so resultant force is 0, Sam might get one measly mark for stating a fact, but completely fails to explain the dynamic relationship of how air resistance actively increases with speed until it finally balances the constant weight. You must decode the command word
first, before your pen even touches the paper. All right, here is your complete physics answering system. Think of this as your final cheat sheet recap. Reaching 100% mark potential relies on 3 absolute non-negotiable rules. Rule 1, command word decoding. Never start writing until you know if you are stating, describing, calculating, or explaining. Rule 2, Peel framework application. Structure your extended writing with point, evidence, explanation, and link to guarantee your logic flows as smoothly as a CEO's board presentation. Rule 3, time management matrix. Use the precise data extraction and step-by-step math formats we just discussed to ensure you maximize your points per minute without rushing and making mistakes like Sam, or over-explaining useless facts like Alex. Implementing these 3 rules guarantees your answers align perfectly with the examiner's lens. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. I am going to leave you with this final, highly provocative thought to test your deep understanding of everything we've built in the boardroom today. Imagine the sun suddenly stopped existing. Its gravity just vanished in an instant. Why would the Earth instantly travel in a straight line at a tangent to its orbit instead of curving inwards or outwards? Think deeply about unbalanced forces, think about the concept of inertia, and apply the PEL framework to structure your answer. Keep practicing, keep strategizing your pitches, and I will see you in the next session.